All right, welcome to, this should be lecture number 3, right? And the first thing that I would like to show you is the course web page. It's more of a course register. It's this one, right? All right, so there's a files folder. In handouts, you're going to get everything we're discussing in class and the assignments. And then in the same folder, there's a subfolder called student submission, and you have a bunch of folders that you have to use for your assignments, right? Whenever you submit, you're going to have to build a file to create a file. And I want you to rename that file with your metric number as your metric number. The file name should be your metric number.py and upload, right? So that there won't be any name clashes. Okay, there's one assignment out, and I should actually retrieve it. Forgot to push. Right, luckily I have uploaded it here. So how visible is this? I wonder why it opened in Xcode. So let's open it in Sublime. All right, so this is the file that you would be downloading, and you have to fill in your solutions, right? So use it as a template, and you have to fill in as solutions. There are 3 exercises for this first one, all right? Each of them has a little description, right? And some examples on how you might test it, okay? Each of the templates looks like this. So it has this word pass here. Pass is an instruction in Python that does nothing. And it's very useful precisely for this kind of situations where I want to show or expecting that somebody else should fill in some code, and I don't want to fill in myself, right? So I would use the word pass there. This word you have to replace with your solution. This is exactly where you have to fill in your code, okay? So for the first exercise, you have to fill in here. For the second exercise, so we're a bit more, because we can't use pass, right? So there's this keyword none, right? So the instruction is here, replace none with your own code. So this none should be replaced by your own code, right? You have to fill in something here to make it work. And similarly for exercise 3, there's this pass here that you have to fill in. And then read carefully, so you would get some instructions on how to test your solution. Okay, the deadline is 1 week from today, just before midnight, right? So you still have time. If you need to ask questions, you still have time. Next time in class or after class, you can still ask or clarify a few things, and then submit later. But don't leave it until then, right? So try to start early. If you run into trouble, ask questions straight away. So send me an email or use the best ways to use the forum in IVLE. Right, I will be notified of any posts that you might put there, and we'll try to answer. Obviously, I will be answering as much as I can without revealing the solution. So I'm going to try to teach you how to fish, but not give you the fish. Right. Any questions for this part? Is this okay? So we're going to have 5 different assignments of increasing level of difficulty, and I'm going to evaluate you based on those and compute a grade at the end. All right. So we don't need to have a final exam. Please, feel free to collaborate in the sense of discuss with each other. But once you have discussed and reached the design of a solution, go and code the solution on your own. So you would avoid any temptation or any possibility of plagiarism, right? It's not very many of you. So as I would go through the solutions, it would be very easy to notice the same pattern or the same, don't do it, right? Please don't do it. I would feel very, very embarrassed to have to penalize you for that. And I'm hoping really not to have to do it at all. All right, questions? All clear? Cool. So back to our lecture. So we have a leftover from last time. So the last thing we have discussed was the bisection search. The bisection search algorithm. So we looked at the recursive one. And by the way, for the homework, only what we have discussed during last week is usable for the homework, right? So we're going to be always 1 week behind, right? The homework for this week relies on the previous week, right? And nothing that we discuss in this week should be used for the assignment. All right, so I'm hoping that this was well understood, right? We understood how we could use it, right? So we use the bisection search function, and we provide another function as an argument, right? And what this procedure does is solves the equation fx equals 0. What's the value of x such that fx equals 0? Finds the root of that function. We have assumed that this function has only one root in the interval given here. So you would have to come up with your own interval that sort of boxes one solution, right? And this is the tolerance, meaning that how much from 0 can we deviate in the value that we find. Okay? And that sort of wrapped up the discussion about recursion. And we are going to move on now and find new ways or learn new ways of performing repetitive computing, right? The important thing about recursion was that we could repeat a certain computation, right? That was the essence. That's why we needed recursion. Just using assignment and iteration, we will not have the ability to repeat a number of times that depends on our problem, right? We will not have the ability to repeat a computation a number of times that depends on our problem, right? And recursion allows us to do that, and there are other ways of doing that as well, and we're going to learn quite a few. So for the time being, let's learn the while loop. All right, it is represented by the keyword while. All right, we have a condition, something that evaluates to a Boolean. All right, and then there's what we call a block. So you see this piece of indented code that is a few spaces away from the first column. It will be executed as the body of the while loop, right? The while has two parts, condition and body. The body can be of any size. We can have any number of statements in there. And last time we argued that it is good always to define a function, a procedure, and put our computation inside that procedure, right? But we're going to deviate right now because we want at least once to showcase the fact that it's possible to have computation without defining procedures. And it's a lot easier to do that with while loops because we don't have to call a function recursively, right? Whenever we use recursion, we have to define a function or a procedure because we have to call itself, because the procedure has to call itself, right? So without defining a procedure, there's nothing to call recursively. But with while loops, there's no problem with that, right? So we're going to see this happening. So no procedure, right? The keyword while, and it performs a repetitive computation. The body is executed as long as the condition stays true. In particular, we're seeing that I initially has the value of 1, right? We're checking whether I is less than or equal to 10. When I is 1, the value 1 is less than or equal to 10. That expression evaluates to true, all right? So because of that, we can evaluate the while body. So we're going to execute the print, and we're going to increase I by 1. So I becomes 2. And then we go back to the top of the while and check again the condition. Is 2 less than 10? Yes. So we go again and execute the body. We print and we increase I by 1. I is 3 now, right? So I go back to the top. 3 is less than or equal to 10? Yes, right? So we're going to keep repeating this, and I is going to go through all the values between 1 and 10. All right? And when I is 10, this condition is still true, and we execute the body of the loop for the last time. We perform the print, and we increase I, and I becomes 11, right? At which point, again, we go to the top of the loop. 11 is no longer less than 10. 11 less than or equal to 10 evaluates to false. The condition of the while is false, and then at that point, we exit the loop. We do what is called exiting the loop. So we go back to the instruction that has the level of indentation equal to the one of while, right? So in this case, while starts in the first column of the text. So we're going to the next place where we have a line starting in the first column of the text, right? Which means here. So we're going to print finish. So this is going to be the output. Right, we see this print being executed for 1, for 2, for 3, and so on, up to 10, at which point the condition becomes false, we exit the loop, and we go right after the loop and print finished. Okay? So this is the most basic thing you can do with a while loop. So let's go here. We're going to have an error. So what we should be doing is open a file, put the text here, F5, okay, test, replace. All right, so we see that it executes. It is very slow because there's a video recording going in the background. And I don't know if you can hear from where you are, but the fan of my machine is spinning very fast. But this is the execution, right? Is this clear the way it works? Is this mechanism clear? Yeah? Cool. So I'm guessing that many of you have seen this before. This print is part of the body. This print is not part of the body. No, it's outside of the body of the loop. Right? All the prints get executed, but the last print only gets executed once. Okay? All right. Let's try to do the same with Fibonacci and learn a new way of computing Fibonacci numbers. Okay? So we're going to print 10 Fibonacci numbers. So by the way, this is generally not the way you should be coding, but it is the way in which many programming books will teach you programming in Python, right? No procedures. They introduce procedures very late. All right. So these examples are precisely for the purpose of you opening, when you open a book and it's a random book on Python, you might see code like that, and you might say, "Oh, we've been learning a different kind of Python." So this is possible. It's not really recommended to code this way. So all the code should be in procedures as much as possible. All right, so let's try to look at this algorithm. What is Fibonacci? Fibonacci is a sequence of numbers um, where each number, so the first two numbers are, let's say, 0 and 1. You can start with 1 and 1, depends on the convention. And each number is the sum, apart from the first two, each number is the sum of the previous two, right? So if we start with these two numbers, 0 and 1, as being the first two Fibonacci numbers, right? What we need to do all the time, repeatedly, is to perform this computation, right? So if this is the current Fibonacci, should be the Fibonacci plus the old Fibonacci, two previous numbers, right? And the old Fibonacci becomes the current Fibonacci. Okay? Is this clear that whenever fib and old fib are, let's say, these two numbers, so let me put more space, and actually I'm not going to put more space here. Let's say that the 1 is old Fibonacci and the 2 is the current Fibonacci. So this is the old fib, right? And the 2 is the fib, right? Well, next round, this guy is going to become old fib, and this guy is going to become fib, right? Is that clear? Because of this computation here. And we want to do this repeatedly so that we can generate all the numbers. Okay? So then we want to then generate 10 numbers. So as long as count remaining is greater than 0, and because I code in a lot of other languages, for instance, Scala, I get this habit of putting brackets around conditions where they don't need to be in Python. All right. So as long as count remaining is greater than 0, right? What do? We already have two Fibonacci numbers from here, right? So we're going to print what we call the current Fibonacci, right? And then we're going to compute the next two Fibonacci numbers in this line. And then I'm going to decrease the count, all right? And then I'm going to repeat. This minus equal is the same as minus 1, right? Plus equal, minus equal, they are shortcuts for these operations where we want to just change one variable, right? We want to change this variable by 1. So instead of typing count remaining twice, we can just save some typing by saying minus equal. All right? Is the algorithm clear? Is it clear that it computes the Fibonacci numbers? Yes? Where? Right. So we discussed this last time, right? First of all, I can give variables different values, right? I can make a equals 1, and now the value of a is 1, and later I can make it 2, and now a is 2, right? That you're okay with that, right? We also discussed that I can say a comma b equals 1, 2, right? Or let's make them 2 and 3, right? And then now a is 3, a is 2, and b is 3, right? And now I can do a b equals b a. That's what you're wondering about, right? Well, in Python just works. So a has the old value of b, and b has the old value of a. You think the computer is too smart? So obviously there are some temporary variables. What happens in the background is tmp1 equals a, right? tmp2 equals b, then a equals tmp2, and then b equals tmp1, and then delete tmp2 and delete tmp1, and right, I can do this sequence of operations in the background and allow the computer to be smart, essentially.
So does this imply that the Python programmer actually understand the argument or carry out the argument from strictly from
Yes. No, so it's simultaneous. When you say left to right, you mean left and right, or left and right? So this is simultaneous. It's not left or right. It's simultaneous, right? If you make the assumption of left to right, then it won't work. Because if I change the order of these two, it will still work. I can say old fib equals fib, and fib equals right. I can write this, and it will still work. This will still work fine. Okay. So you can't assume that it's left to right or right to left. It's simultaneous, right? And what happens is exactly some temporary variable names are invented, all right? So then all the values are taken into temporary variables, and then from temporary variables back into the variables, and then the temporary variables are destroyed. Clear? All right, so let's execute this. Okay, so there's something else we did here, all right? If you remember, whenever we had print will type a number, or print a number on a separate line. So our previous examples of print would work like this, right? One output per line. But now we're learning that we can add this named argument, and we're going to talk a bit more about name arguments later, right? When we say what should happen after all the printing, what character should be used after all the printing, right? And you might know that there exists such a character called end of line, which is encoded by \n. So if I use \n, I will get the usual behavior, right? So if I don't specify an end, the default value of end is \n. But I can replace this by a space. And at this point, after every print, instead of printing a new line, we print a space. And this is the space that you see right here. This is one space. This is another space. And guess what? There's another space right here as well that was printed after the last print, even though you wouldn't know that it's there, but it is. Okay, is this algorithm fine? Okay, with everybody? Any questions here? Cool. So We're going to go back to defining procedures, right? So let's rewrite the bisection search algorithm, all right, using a while loop. So we're going to have the same arguments: a function whose root we want to find, all right, a low limit, a high limit, and a tolerance, right? The low limit and the high limit box the root. We're assuming that between L and H there's only one root, right? Otherwise, it wouldn't work. And let's see how we can compute this. So we start by computing the median of high and low, all right, and computing the value of the function at the median point, okay? And then, as long as the distance between high and low is greater than the tolerance, we keep crunching, right? As long as the distance between high and low is greater than tolerance, we keep crunching. Also, it may be the case that we might find the root by chance, right? We might find it by chance, right? So it may happen that this value is already 0, which means that we have found the root accidentally, right? So if we have found the root, we don't need to crunch anymore. So we keep computing when obviously high and low are far apart enough, and as long as this v is different from 0. Otherwise, we would have found the solution already. So what do we do then, right? If the root is, so let's understand what's happening here, right? If v and fh times fh is less than 0, it means that v and fh have different signs, right? It means that the root, the 0, is between them, right? Right? Okay. And if that happens, so if the root is between v and h, between m and h essentially, right? Then there's no root between L and M, right? So I can move the L to M. There's no root between L and M. I have to focus my search between the current M and H. So I move the L up to the position of M, and our default algorithm will search for solutions between L and H, right? So from L I bring to M, because between L and M there's no solution. Otherwise, it means that the root is where? Is between L and M. Between M and H, there's nothing here. So I have to focus my search between L and M. So I'm going to bring the H down to M, and I'm going to keep focusing my search between L and H, which is the previous L and M. All right? So what do we do now? You see, this if is in one statement. Right? So we go and execute the if, and either we execute this or we execute this. Once we are done with the if, whichever branch we might have executed, we're going to go and compute this. So we're going to compute a new value of m between the new h and the new l, or the new l and the new h, right? We're going to update v to be the function value at the new median, and we repeat. So this is the while instruction. The return is not inside the while. The return is indented as much as the while, and it's not part of the while because of that. Everything that is indented more than the while is part of the block. So this part will keep repeating, crunching and crunching and crunching until this condition here becomes false, right? At each step, either H becomes lower or L becomes higher. There's no way around it. Either H goes low or L goes high, right? So they keep going towards each other, and at some point they're going to meet or to be very close, be within the tolerance interval, and then we can stop. Okay, is that clear? Once we have exited this while, we can go and execute the return. And the return value is m, which is the median between my current L and my current H. And that is a good enough approximation of the solution. Is this clear? Yes? All fine? All right. So let's see this one. Uh, okay. So what happens now, because we have a procedure, is that the definition is processed, right? The definition is loaded, but we haven't executed any particular computation. I'm just going to go back and steal one from here, right? So this will compute the uh, cubic root of 10. This is definitely not a good value. Oh, obviously, because we're saying 100 and 0, not 0 and 100, right? So we're going to talk soon about garbage in, garbage out, right? So this computation is useful as long as it is used as intended, right? So if it's not used as intended, then it will produce garbage. So what was wrong with the previous expression? We set the low to 100 and the high to 0. Obviously, the low has to be smaller than the high, right? And that's the reason. And we can verify this by simply saying this value to the power of 3, and you can see that's very close to 9. Obviously, we can increase the tolerance, right? And we're going to get something that is probably closer to 10. Oops. What have I done? I pressed Command B. I have no idea what this is, but it doesn't seem to. Yes, please. Yeah. Again? No, it can be the gradient between low and high is positive. Yes. Yes. Yes, because we are performing this test, right? So one thing we could do to change that is to do math.amps, and that will help, right? So then I don't depend on the gradient being positive. Let's see if this. Okay, I think I'm going to have to close this one down, which I can't. Interesting. Okay, back to normal. All right. So let's learn a new statement. It's the break statement. The break statement allows us to break from loops early. All right. So what happens here is that the exit from the while loop happens right at the end, right after executing this statement. Sometimes we don't want that to happen. We will detect some condition in the middle of the while statement and we say we don't need to execute the rest. And the break statement helps with that. All right. What is particularly annoying in this version of the code is that we have to repeat these two statements. All right. So you see this statement here, and then exactly the same statements here. They're a bit indented, but repetition in Java is something that we don't like. Okay. So let's try to mash them together. All right. So we're going to repeat some computation. We don't know how long when we have to stop it, right? So for the time being, let's not focus on the condition, right? What do we have to do? Exactly as here, we have to compute first the median and then the value of the function at the median, right? Then we have to have this condition that we used to have here. We need to have it. There's no way around it, right? But notice now that we're doing the negation of that. Okay, let's make it back the way it was so that there's no confusion. And you see the while condition, and what we have here exactly the negation of that. Is that clear? Yes? I think you're jumping the gun. So you're trying to propose a different solution, or what? You could, but what's the point of performing a computation that you don't need? Right? So let's look at what's here, right? So this is the negation of this while loop. So if h is close enough to L, this is what we're saying here. If h minus L is less than t, h is close enough to L, right? Or by chance, we have discovered a root. V being 0, it means that we have discovered a root. The root, because we're assuming only one root, right? Then at that point, we're done, right? So we don't need to keep crunching. So this break will take us out of the while loop and directly to the return, right? So we're just putting this test here, and if this happens to be true, we're doing the right thing. We're doing a break, going to the return, and returning the value. If that's not the case, then we check. We have to shrink our interval, right? Either we increase the low or we decrease the high, right? So we have to see which. So if v times fh is less than 0, it means that there's a root between m and h. So we're going to increase the low. Otherwise, it means that there's a root between low and m, and then we're going to decrease the high, right? And then what do we need to do? Well, what were we doing here? We're going to compute this again. But by virtue of the while loop, whose body is this, after we're out of the if statement, we're going to repeat because we're still inside a while loop, and we're going to execute these two, which is exactly what we were doing here, right? So we're performing exactly the same sequence of statements, right? But we don't have to write those statements twice. Okay, now, what am I going to put here? Well, I will never exit from the loop at the bottom. Therefore, I don't care what the while loop has. It might as well indicate forever, repeating forever, right? True will never become false, and then means that it's repeating forever. That doesn't really mean that the while loop is going to execute forever because we have this break inside. Is this clear? Everybody? Then it executes forever. It never ends. and you have to go into the terminal window and kill the process as I just did. Okay? Which you'll do a lot. So there will be a lot of bugs. So are we okay? So believe me that this code, if we execute it in Python, it will be exactly the same. It will behave exactly the same, right? And you can do that on your own. Are there any questions? Some of you are still quite puzzled. Uh, it doesn't matter. All are equally good, right? So there's no one way to skin a cat. Okay? Remember that. I prefer one that is correct. Um, what would I prefer as a professional coder? Something completely different from this, and hopefully we'll get to see some of that later in the course, which is completely different. So there are many, many ways of doing repetitive computation. Doing repetitive computation is the essence of programming, right? Doing sequential one-time computation is not that interesting. All right, but there's many, many ways to do that, and these are the most basic ones. Okay, so for your assignments, one that is correct. So try to get one that is correct. Sometimes I'll say no recursion explicitly. That's the only restriction that you're going to have. So sometimes I'm going to ask for recursion explicitly. Sometimes I will not allow a recursion explicitly, and then that will be the only restriction. But when it comes to ways of writing while loops, the sky is the limit. I mean, we're going to learn the for loop very soon, and then we're going to learn iterators and generators, and they're all ways of doing the same kind of thing. All right, can we move on to the next one? Okay, so let's look at what's going on here. After this break, the only thing we'll ever do in any of the executions of this bisection search is going to be this return. Do you agree with that? Once I reach the break, the next thing is going to be the return, right? And we are inside a procedure, and the return statement exits the procedure. We know that, right? It's essentially the way to go back to the calling program, to the calling place, and return a value. So then why not replace the break directly with the return? Should be possible, right? So doing this is called the 1.5 pattern, which you're seeing here. All right? And this is what we're doing here. Instead of having a break, we're just doing the return M. So if we are inside a procedure, and only if we are inside a procedure, we can use the return inside the loop to break out of the loop. All right? Cool. All right. Let's look at a different way of solving equations. All right, which is called Newton-Raphson, and it's a very ingenious method. Newton's method. All right, I want the picture. So, one way of approximating the root is by bisecting, right? I'm taking an interval and I'm assuming that it's in the middle, and check whether it's in the middle, and then decide to shrink to the left or shrink to the right. A faster way to do that is to consider one point instead of two, just one point, which is the initial approximation, and draw the tangent to the graph. And the tangent to the graph, if you remember, the slope of that is the derivative, right? Everybody knows that? Yes? 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 Nod your head if you do. Okay, cool. All right? So then we follow that tangent to the place where it intersects the OX axis, and that's the next approximation. And then we keep going and going and going. And as you can see, I mean, this is a very well-chosen graph where it appears that it converges very quickly, right? Much quicker than it have done with bisection search, right? And in general, that's true. So this is faster, but it's not always faster. There will be cases where it's worse. And let's try to do that. Let's try to do exactly the same thing. The interesting thing that we can do now, let's stop the animation because there's already plenty of computation going on. So the interesting thing is that we have a derivative function already computed from last time. Remember? All right, find previous one. So here, right? So I'm going to take this guy and put it here. And then let's go back to the end. And there's a formula there. So I won't bother to invent the formula. This is the formula, okay? So we start with one approximation, and then the next approximation, xn plus 1, comes from this formula, right? Where f is the function whose root we want to find. Is it clear? So all I want to do is implement this formula in Python. This f prime is the derivative, and we have a function that computes the derivative. Cool? So this is the formula. You can look carefully at the formula side by side with the Python expression, and reassure yourself that it's the same. So in this code, A is the initial approximation of the code, of the solution, right? And then we're computing the next approximation. And every time we're going to compute a next approximation from the current one. And we're going to keep going as long as, right, the next and the current approximations are not within the tolerance. As soon as they are within the tolerance, we can stop the computation. And we stop it by the 1.5 loop pattern, which returns from the middle of the loop. Okay? So notice the very interesting thing that we're taking advantage of a existing procedure inside the new procedure that we're writing. Okay? This is a very important thing. This is exactly how coding should be done. We should code in small chunks. We should code procedures that have a very well-defined meaning, and we should build the code bit by bit, little procedure by little procedure. That makes the code very easy to understand. So I'm going to, and actually let me take, okay, so I can load this. Okay, and obviously, completely unsurprisingly, we're going to compute logarithm of 10. Yes, so we need x, right? So I'm going to import everything because I think there might be other functions. There's ups, there as well. So I'm doing something that I shouldn't be doing normally, but, and then this will produce logarithm of 10, right? So log 10 is this, and you can see that the two values are very close. Okay, so you can see them side by side. All right. So the important thing that you need to understand here is that we're making use of a function that we defined before. We're making use of a piece of work that we have done before. All right? Yes. There is a derivative where? I don't think there is, but do you see one? I don't see one. So I'm sure there will be packages that have that, but math doesn't have it. That's all it has. Yeah. That's all. Which is a lot, really. Right? Because it has the gamma function, so you can do statistics with it. You're happy? Good. Good. And this is what I was hoping to go through in the first lecture. Okay. And with more advanced students, I will probably help. Since we have some time, let's start talking about scopes and abstraction, right? So let's talk about using functions not just for defining as mathematical functions. Let's try to understand the difference between functions and procedures. And there's two things that we want to understand here: scopes. So scopes have to do with hiding information, right? We want to hide information because we want to avoid cognitive load that somebody reading our own code might have when they do, right? Or even us, you're going to experience this, right? Reading your own code 2 weeks later or 2 months later. It looks like you forget a lot of stuff about that code, so it looks foreign to you, and it's important to compartmentalize the information in such a way that you take it in small bits, right? Otherwise, you end up with code that is not reusable. It's called write once. You write it, and then you try to read it and don't understand it, so you decide to throw it away and write a new one, just because you can't. It's faster to write a new one than to try to understand the old one. All right, and this is the essence of abstraction. Abstraction means hiding information, making information less apparent, looking at the big picture. Okay, so this is what I'm trying to tell you here. The reasons why we want to have functions and use them in this form. Okay, and we want to perform abstraction again to avoid the cognitive load. One thing that we discussed last time about using procedures, which is a reminder here, is we want to avoid duplication, right? So that's one thing that functions and procedures allow us to do. Now, in everything we do, we keep relying on predefined built-in functions, right? So it's probably a good time to talk about the standard library a little bit. We introduced bits and pieces of the standard library all over the place because we didn't have another way of doing things. So at least now let's try to understand what is this about, right? So Python comes with a huge library, right? Do you know what a library is? Yeah. Okay. Cool. So it's pretty much like a regular library, right? Because the library's code is text, right? But just that it's code. So it's available and it can be loaded on demand. And those are useful pieces of computations that you can use in your own programs. And we've been using math quite a bit, right? The important thing is that we have to import it explicitly, because every time we load a library component, it takes up some resources, and the machine has only a finite amount of resources. So you don't want to uh, be wasteful, right? You want to use only what you need. So once we perform these imports, right, which we have seen already, these functions become available readily, and we can use them as if they were there from the very beginning, right? So we can use abscent, cosine, logarithm, exponential, and a lot of such um, functions. And you should wonder, right? One, could you have written, for instance, the sine function? Obviously, right? How would you write the sine function? If the sine function didn't exist, how would you write it from scratch? How do you write cosine then? So, what are the basic operations of a computer? A computer: addition, subtraction, multiplication, division, right? That's it. So, if you know how to add, multiply, divide, and subtract, how do you compute something like sinus? Louder? But this is, how would that be? How do you come with the hypotenuse and the opposite to? So Taylor series. Remember Taylor series? Who hasn't heard of Taylor series? All right, Taylor series. There they are. Okay, actually we wouldn't be using Taylor series. We would be using Chebyshev series. So anyway, any function that is continuous and derivable, indefinite derivable, is we can write it like this, right? This is a polynomial. Okay, and it turns out that it's a polynomial that converges towards the value very quickly. So we only need just a few, right? So just a few terms out of this. So notice that fa, f prime a, f double prime, f triple prime, they're constants, right? And for instance, if I take a to be 0, I know sinus of 0, sinus prime of 0, sinus double prime of 0, right? So I would have to take a finite number of these terms, and that would be my approximation of sine or cosine, right? Any function, logarithm, exponential, you name it, can be done in this way, right? So it so happens that for trigonometric functions, this is very slow converging, and there are other kinds of series that are similar, right? So a series is an infinite sum, but it so happens that the infinity from a certain rank on is actually a very, very small number, so I can ignore that. I only need to compute a finite number of terms. So this is how we would compute all those functions, right? Now, even though it seems relatively easy to understand what's going on, if you think in terms of the computation that you would have to perform, it's a relatively sophisticated piece of code, right? So if you have to do all this sum in a piece of code, it's going to be quite a bit of code, right? So the good news is that you don't have to. It's already in the library. So it's very easy to understand how to use sine, even though it's not so easy to write it yourself. And that's a very important aspect of abstraction, right? Whenever you want to write code and you're thinking about abstraction, right? You want to write code that is easy to use, even though it's complicated to write. You want to give it to somebody else, and those people don't need to understand the computation in order to use it. If you think of that, we use abstraction all the time. A car is largely an abstraction. You learn to drive a car, and what do you know about a car? It has a steering wheel, a couple of pedals, and the stick, right? Depending on whether it's a manual transmission or not, right? But how many? I mean, I don't know if you drive. You're probably too young to drive on a regular basis. But maybe some of you have a driver's license. How many of you have opened the hood of a car, right? So I haven't done that for 20 years. So when I was younger, I had cheap cars, right? And I had second-hand cars, and I didn't have money to take them to the to the shop. I would do some repairs myself, right? But I haven't done it for a very long time, right? So even for me, even though I know what's there, I don't have to care. There's an engine, and there's a very complicated brake system, and with nowadays cars, there's a lot of electronics and computer components inside a car. I don't have to care about that. All I know is that there's two pedals, a steering wheel, and some controls, and an entire car responds, and it's very easy to drive, and it's relatively easy to learn how to drive, right? It responds to my commands without me having to know how the car really works, right? Is this understood? So that's an example of abstraction. We have such examples all over the place. Many of the appliances that you find around the house, the TV, similarly, right? Turn on the remote. You have that little remote with a few buttons, and you have no understanding, or maybe some of you do, right? But you don't need to understand the how a TV is built in order to use one. Is this clear? All right. So since there's 15 minutes, let's go through this example so I can leave you with a puzzle. All right. Oops. So we're going to load this function. And I'm going to define a variable. Oh, sorry, a equals of 10. So now I'm going to say a of 2 values to 12, a of 5 values to 17, right? And 13 goes to 30. And I'm going to make another variable b, which maybe has an initial value of 100. And I'm going to say now b of 10 goes to 110. b applied to 20 goes to 130. Now if I go back to a and say a 15 goes to 45, right? So it seems that this is, a seems to be a function, right? Because I can apply it to some arguments. But then it's a very strange kind of function, because every time I apply it to the same argument, it returns a different result, right? If I say a applied to 15 again, I'm not going to get 45, I'm going to get 60, right? So we're used to functions when we apply them to one argument, every time we get the same result back. This no longer happens. So this is a significant difference between procedures and lambdas. We can do this with procedures, we cannot do this with lambdas. I was warning you last time that this is something that happens. Now, you see this variable value here, right, being defined. Well, if I try to find out the value of this variable, if we evaluate it, there's no such thing, right? So the one thing that we have to understand is that because this value is defined inside the procedure, you see it's indented from the procedure, that value is local, it's hidden, okay? So this body of the procedure is also the scope of the procedure. Scope means range, means territory. right? So the place where this value is defined is what I have highlighted, and the main space, the main interpreter doesn't see that. So perhaps this, I shouldn't have used value here, because it's you see value here and you're wondering the value of what. But value is just a variable. Okay, it is not defined. Now, let's see how this works. What are we returning from this function? So when I say a equals make adder, what am I returning? I'm returning ink. What's ink? It's a procedure, right? So this, whatever is the result of make adder, it's a procedure. It's something that can be applied. And as a result, I can write a applied to 2 and not get an error, right? It is not a function though, because functions have this ability of returning the same result every time they're applied to the same argument. It is not a function, okay? So what happens here? Well, I was telling you that this value is defined only here, but actually it's less than that. It's defined here and here, but it is not defined inside here. But we can force it to be defined there by using this clause, non-local. We're saying, oh, let the scope of this extend over here. All right? And then what are we doing? We are incrementing value with this x. So x will be sometimes 2, sometimes 5, sometimes 13, right? And what we're doing is whatever x comes in as, that value gets added to the local state. This becomes like a state. It's something that has memory. Okay? And then we're returning that state. Okay? So we can build a procedure with state. There is no way we can change this value except by using ink. Value is hidden. So at this point, if I say value is 1000, yeah, that works. I have a value of 1000, but when I evaluate a applied to, what was the last value of a? 60, right? So if I say 20, I'm going to still get 80. So the value that I have defined outside and the value that is defined inside here, they are different. Moreover, I can define two such procedures, B and A. The value defined for A is different from the value defined for B. They are local to that. So if I go and evaluate B 100, I'm going to get 230 that has nothing to do with the 1000 that we have defined outside. Okay? This is a very tricky way of programming. All right? And it's something that is generally not recommended. And I don't expect you to practice it. All right? I want you to understand that this is possible. Okay? So, this kind of assignment is called mutation. And this kind of code is called mutable code. And if you look at programming practices, modern programming practices, most people advocate immutability. No mutation. All right? So you expose yourself to various kinds of bugs if you do that. However, every once in a while, this is a very useful feature. This is a very useful hack. All right? So it's something that normally you would want to understand and master possibly, and use it only when it is absolutely necessary to use. Okay? So remember, with great power comes great responsibility. This is one of those One of those situations. Right? Yes. So if this was missing, let's say I comment this out, right? This value and this value would have nothing to do with each other. They would both exist separate from each other. There would be two instances, two separate variables with the same name. Okay? So the way to connect this and this is by saying non-local. This is a weird aspect of Python, and it is to protect yourself, to protect coders from exactly what I was saying, to protect them from mutation. All right. So you have to explicitly say that you want to mutate something that is not that immediately in your scope.
Does it work? Because there is a function inside.
Yes.
So does it work if, for example, I just have one function and I have one variable inside.
What do you mean a variable inside a variable? That doesn't exist.
Like, for example, like we have fx.
Uh-huh.
Instead of only fx, we have bracket. So
You can't have that in the definition. So you would like to define something like def f gx. No, it has to be gx.
so in that consecutive, we can just use that kind of thing to
So use again what?
also the first variable will be the initial value, the second variable will be
Okay, initial value x and
x. So the rest is similar because we have another
and you would want to, so we say value equals I, and then what do I do next? Yeah, you could in principle, but I still don't see where it would take you. Well, why don't you try to come up with a piece of code on your own, and we can discuss that. Okay, so this is what I have for today. Please take a look at the assignment early and figure out whether you might have any potential problems with it, and let me know. All right. Any questions? If you want to linger on and chat some more, please do that. Otherwise, class dismissed. Thanks for coming. See you next time.